So my name is Joseph Gonzalez. I'm a co-founder of Dato. I'm also a faculty at UC Berkeley. And today I'm going to try to tell you about some of both the research I'm doing and some of the cool stuff we're doing at Dato. Particularly, I'm going to talk about the design of intelligent services, and really how we take machine learning all the way to production. So if we think about machine learning in one picture, I think this kind of captures what we do in machine learning. In a sense, we take data, we go through this process of training to build a model. You can think of machine learning as going from maybe a table of user item rating, triplets, to construct a function. Given a user item pair, you could estimate the rating for that particular user item pair. So this is a story of machine learning. And if you're here today, I guess you've probably heard a lot of these different companies talking about technologies around solving this critical problem. And in many ways, it's become a key part of what we think about when we think about data science. But today, I want to talk about a different side of the picture. And I think the side is perhaps actually more exciting, both academically and industrially. In particular, that's the question, what happens after we train a model? And so if you're like me, an aspiring professor at Berkeley, we write papers. That's the end result of our model, right? So the consequence of models in many ways in the history of machine learning has been the development of these academic pursuits. But we had bigger aspirations in building these models. We often believe that someday these models might be used perhaps in a dashboard or in a BI tool to make predictions about the future, to help people make better decisions about the data that they have, right? So that's a bigger goal for machine learning. But actually, there's a new kind of goal that's become pretty central to the adoption of machine learning today. And that is, these models are being used to drive actions, right? And so literally, it could be driving a car, right? So that's the implications of these models. Not just reports, but things that connect to the world. And so when I think about driving actions, I think about things like suggesting items at checkout. So if you're in Amazon, you're about to check out, what items should you buy? Right? Another one might be fraud detection. Right? So you're a credit card company, and someone's about to make a purchase. Is that purchase fraudulent? Again, you need to make this decision quickly. You need to make it for that user. Or it could be in the context of cognitive assistance. Maybe something like Siri or Echo. Again, you're talking to a device, and you're looking for a response in real time that's understanding your context and making predictions about what you're asking. Or we could be the Internet of Things. Maybe you're a GE. You're selling sensor systems. You want to know if this particular turbine is about to fail. You need to make a decision quickly so you don't lose a particular part. So in all of these stories, we have this need for low latency, right? So we have to make predictions quickly. We also have this personalization aspect. We're not making predictions about the whole world, but we're often trying to make predictions in a particular context, about a person, a jet engine, maybe a transaction. And finally, we're living in a rapidly changing world. The idea that we can train a single model and have that work through all time is simply wrong. It's a fiction. Our data is no longer static. We need to think about models that live in this dynamic context. Right? So I want to take a new picture of machine learning and of data science. I want to start to think beyond how we go from data to model, how the model emits action, so how it connects to the world, right? And this could be driving a car. And how those actions actually come back to affect our data. So as we make these decisions, we change the world, we actually influence the data we see in the future. And this bias becomes a key part of how we think about and how we build these systems. So in going from machine learning, this process of taking data to model and starting to think about this bigger picture, we're starting to think about what I'm calling intelligent services. These are applications that connect back to the world. And so today I want to talk about what intelligent services look like and some of the technologies I've been developing in this context. But to do that, I want to give an overview of what I think is sort of the picture of an intelligent service today. And so let's imagine a scenario where we have a user, and they're clicking on things that they want to buy next or the next song they want to play. And so that action is going to trigger something in our web serving tier. So it's going to send perhaps a REST request and say, hey, I want to get K items that look like this thing I just clicked on. Right? And that's going to go back to what is today represented as this intelligent service box. And it's asking to be a top K query. Return K similar things to this item that was just clicked on. In order to answer that question, we might have to find the model. So we might actually do a database lookup to find the model. We might also have to do database lookups to get the features about the items and perhaps the user. And then doing all that, we're going to do some piece of gratuitous math or animation, describing some calculation that's going to take that data, fuse it, and render a prediction. Now, we're not actually done, right? So the prediction is still these kind of description of the similar items. To render the content, we might have to go back to the product info, get the information about those products we've selected. And then finally, we're able to render content for the user. So it's a fairly involved process of going from a question to an answer. And in an ideal world, we get some feedback. Maybe we made the user happy. And that feedback comes back to our web serving tier, and perhaps goes back to our intelligent service, which might run a bandit calculation or some online gradient descent to update the model. And finally, that would actually trigger updates in our underlying data stores. Right? So we have this forward-backward movement of data in a system. We have this need to reason about things that are changing. And so I want to talk about how we address those problems. And I'm going to do something a little bold. I'm going to actually talk about two technologies that I've been developing that in some ways compete at solving this problem and take different approaches. And I'm going to try to contrast those approaches, use some insight into the design of these systems. In particular, I want to look at Dato, so the company I'm a co-founder of, has a technology called Dato Predictive Services, which is in a sense a commercialization of this idea of a production system for serving machine learning. And I want to contrast that with the project I've been developing at UC Berkeley as part of the AMP Lab. And this is a project called Velox, which is an open source research project exploring ideas in the context of serving models in production. All right, so to do that, I want to frame this discussion in terms of three dimensions. So one is responsive. These intelligent applications need to respond in real time to changing worlds. They need to do that in a highly available context. For example, if Google were to lose its ad serving system, the ability to make intelligent decisions, that would have a very big impact in the bottom line for that company. So these need to be fast and need to be available. They need to be adaptive, right? So we need to think about these things as constantly training our models. Once you've trained a model, it's already out of date. So how are we going to incorporate feedback in these technologies? And finally, they need to be manageable. In many ways, this is the less glamorous of the dimensions, but actually a critical one. How are we going to deal with many models, often developed by competing teams for similar tasks or related tasks, the dependencies they impose, and the issues they create as they change over time? All right, so first I'm going to talk about what I mean by responsive. And so across the board, talking to a lot of companies in the Bay Area, we found that the need to make predictions is typically bounded by something around 20 milliseconds. So when we want to render a prediction, whether or not I like a particular item, that needs to be done in roughly 20 milliseconds. Now, I want to tell you why I think that's particularly challenging, and maybe even also interesting. So we think of the models we want to render. They're not just linear models, but these could be decision trees or complex ensembles that require non-trivial amounts of calculation in order to get to a particular prediction. Now, there are opportunities there, and I'll come back to how we can leverage the structure of those models to actually speed things up. But at least naively, it's a complex computation process. Likewise, with deep neural nets, there's a really exciting development in machine learning. It actually presents a new challenge because the calculations required to evaluate those models are actually non-trivial. When we think about queries, it's common in machine learning to think it's a classification or regression task. But often that's not what the end user wants. They want the top K similar items, or they want a segmentation of the space. So our queries are much richer than simple evaluation tasks. And to address these queries, this 20 millisecond envelope can be very hard. And finally, there's the question of the features. Where do we get the input for these models? And often that itself is a database lookup, adding to the latency of the system. So now we have to balance all of these challenges and try to make this 20 millisecond deadline. And we want to do that under heavy query load and with system failures. It needs to be highly available. So I want to talk about the common solutions that people are using. So there are two, roughly. One is to build faster online model scoring. So evaluate these models quickly by optimizing that function evaluation. And there's some cool ideas in how you can do that, and I'll talk a little bit about those in terms of the research projects. There's also a question of prematerialization. So a very common strategy to serving models to simply evaluate the model entirely offline. Pre-compute all the predictions you might need, put them in a database, and look them up quickly. But that presents challenges when the space of questions I might need to ask is unbounded. Or, for example, when it's very large and I simply just can't afford to do all those calculations, especially as my model is changing. So Dato actually tries to address both of these. So when we think about how we score models more efficiently, we built our scoring system on top of a very fast evaluation framework. So we knew that latency would be a critical challenge here. So we optimized the S-frame to deal with low latency serving, as well as these high throughput situations. The other thing is that we looked at prematerialization as a form of caching. So I think this is actually kind of a neat strategy and one that we've also adopted in the research project. And that is to take the materialization and actually treat it as a query lookup. So every time I make a query lookup, I actually do the calculation there, and I save it in my cache. I share it across machines. So I'm actually going to use a distributed cache, which means that as I add more machines to my cluster, I actually bring down the latency. And because it's a prematerialization strategy, we also ought to do automatic cache warming, which means that instead of just placing your model in production and missing the cache continuously, we actually keep a log of the things that were recently evaluated. Pre-compute the cache entries before your model goes into production. which means you've already prematerialized the most likely terms. And so we can think of caching as a form of smart materialization. So it's a really cool strategy that you can use to speed up the evaluation of models. All right, so it's actually pretty impressive. So I have some numbers on what we were able to achieve at Dato. And I should say it didn't start like this. So it was actually a non-trivial effort at these times down. So if we hit the cache, it's around 2 milliseconds to render a prediction for any model, right, which is really fast. If we miss the cache, this was the hard part. So we have simple linear models. We can get it down to 5 or 6 milliseconds. This is actually some of the overhead in setting up the internal data structures just to do the evaluation. But if we take more complex models like random forests, and these are fairly large models, I think hundreds of trees, we're able to get it down to 7 or 8 milliseconds. And more importantly, if you think of the P99, we can get that down to 15 milliseconds. So this is kind of the tail latency we might expect from these sort of systems. This makes it usable technology. So you can serve random forests in real time, evaluating them in real time. All right, so I told you I would also talk about my research project at Berkeley. So Velox takes a slightly different approach to how it thinks about these intelligent services to begin with. Fundamentally, we think of it as personalized or contextualized model serving. Rather than having a joint model for everything, we build separate, or at least logically separate models for each user or for each session. We do that dynamically. And the way we do it is we look at a model not as this black box from input to output, but actually as something we can decompose. And in doing this decomposition, we can peel off the top layer and treat that top layer of this model as something that's kind of unique to the user. So we call this the split model approach, where the thing on the left, the thing that looks at the image and reduces it to its representation of cats and dogs and textures, that's something that's shared across people. And the thing on the right, the thing they might say, you like this image or don't like this image, that's actually unique to a person. And that's something that's then associated with each of the people in our world. Now, in doing this decomposition, we actually gain something pretty neat. So our feature model on the left, person on the right, when it comes to doing the feature calculations, we can now share those calculations across users. So again, we have this idea of caching, but here we're leveraging imposed similarity across users so we can reuse the feature evaluation across multiple users. We've also used anytime feature evaluation. So when a feature doesn't get back to us in time, perhaps a database is running slowly, we can introduce a default value and allow the model to continue to evaluate. And you can analyze the risk associated with that, at least in the very simple context of linear models. And we also were looking at ideas of approximate features. So this is still pretty active research, identifying ways of discretizing our feature space so that similar items are treated identically with respect to our feature evaluations. Okay, so that's the story of Velox. And now I want to talk a little bit about adaptation. So I talked about responsiveness. How are we going to deal with change in the world? And one of the first things that we've noticed in both these projects is how change happens. So it's tempting to think of change as this continuous thing. You're just going to retrain your entire model. But the realization is that change happens at different granularities, both in terms of data and the rates at which it changes. So we think about the entire population. Things at the level of the population change over orders of months. And as we start to think about individuals or items or even sessions, things change more quickly. So if I'm shopping for my mom one minute, I might be looking for one kind of thing. And the next minute, I change my context, I'm looking for something different. We want our models to respond to this kinds of change. So the neat thing, if we think of this from a statistical perspective, if we look at the left side of the picture, this law of large numbers sort of suggests that these models are going to change slowly. And we should be able to leverage that. In fact, we can rely on efficient offline training, high throughput systems to address this kind of change. If we look at the picture on the right, these are things that are changing. In a sense, even though we have huge amounts of data, vast amounts of data, when we think about a person or a session, we actually have very little data. And so we need to be able to respond to that change. In fact, when a user first comes on, we have no data. We need to learn very quickly about that particular user. And so here, we need low latency online systems. And we're also going to be sensitive to sort of feedback loops that are a result of bias in these small data sets. I don't know if everyone's probably used Amazon. I went shopping on Amazon just once, and I looked at a camera, and this is what happened. Right? So my Amazon homepage is insisting that I would like camera items. Right? So just based on one click, they already learned they should recommend cameras and probably camera bags. Right? But the problem now is they stopped showing me other things. Right? So they're starting to learn less about me. Right? And so they would not know that perhaps I like kites and archery, which I do. That's not captured, and there's no way for me to communicate that to them. So we have this problem of exploration and exploitation. It's a classic problem in machine learning. It's a trade-off. We need to start to think our systems that can take actions on the world can adversely bias the future data. And so how do we deal with that? And so if we think of this dimension, on one end we have exploration. If I show random things, I'm going to at least have a chance of seeing more. In fact, there's strategies to improve that dimension. Likewise, if I just show things that the model is insistent I like, I won't learn as much, but I could actually get better results because I'm going to show at least perhaps more relevant things. And so when we start to think of this trade-off, it moves us again out of this batch processing world and starts to think about machine learning as it's being served in real time. So Dato has a pretty neat solution to adaptation. So when it comes to training these offline models, we're able to use the S-frame framework. So GraphLab Create, our model training technology, and we can train on large amounts of data actually relatively quickly. So even though we're going to train across the entire data set, we can do it on the order of hours or even tens of minutes. But one of the things that we did that's, I think, pretty exciting is we've introduced bandits. So one of the things that Dato lets us do is play a bandit trade-off, where there's an online algorithm that's going to automatically compete with different models and allow us to adapt to user feedback. And I'll show you a demo of that in a few minutes. All right, so if we switch to Velox, we took a slightly different approach. So what's pretty neat about Velox is this model decomposition allows us to capture change at different rates at different parts of the model. So if we look at it mathematically, we can treat this model as a function x, or a function of the input x to some prediction, the output of this evaluation. And this feature function on the left, f of x, is parameterized by some theta. This is a representation of the featureization of that input item. This is something that's averaged across everyone, and therefore changes slowly, and so we can leverage offline training. So this piece on the left, we actually train using Spark. So it's an offline training framework. In contrast, the piece on the right is unique to each user. And this is something that's a simple linear model. And so we can now apply online algorithms like stochastic gradient descent to optimize this efficiently in real time as we get feedback. And because it's a simpler model, we don't need as much data, so we can safely do these kinds of optimizations. All right, so I talked about how we address the challenge of responsive, adaptive, and now manageable. So I'm going to tell you some of the interesting challenges and what I think makes manageable a unique problem. And I'll tell you about some of the solutions we have, but I claim that this is one of the open challenges that there's yet to be a good academic or really deeply solved industrial solution. All right, so when it comes to management, I have this interesting phenomenon where, as a consequence of the excitement in data science, there's a lot of people building models to solve problems. And even at a single company, you might have teams of people competing to try to build a better solution or build solutions to two closely related problems. And so what that looks like is you can have these complex model dependencies. So suppose I'm interested or have a company that looks at cats or is interested in photography. So I have a photo, and one of the guys on my team might train a cat classifier, maybe using a deep neural net. Right? And so this thing will take a picture and tell me if there's a cat in that picture. So that's a useful model, and that might go into one of the products that we ship. And then another team comes along, and maybe they're interested in an animal classifier for a different product. Well, having a cat classifier is a pretty good feature for your animal classifier, so they're likely to plug that feature into their model, right? And now they're building another product that's going to predict, is this an animal? And then finally, we might have something like a cuteness classifier. So someone comes along, I'm going to build a cuteness classifier, and I will depend on the image, but I might also depend on whether or not it's an animal. That's a good indicator of cuteness. And so you have yet a third product that, again, is making a prediction. Right? I have an opportunity now to leverage the shared structure of these problems so I can reduce the computational cost of serving these underlying models. But I also have a unique challenge because if I improve the cat classifier, I may not actually improve the quality of the cuteness classifier. Right? So things that might have looked cutely like a cat but aren't really cats may no longer be identified as cats and therefore actually lead to worse results in the cuteness prediction. Right? So these dependencies are critical challenges that we need to address. We think about management of the whole ecosystem of models. So with Velox, one of the things we've been doing is starting to track feature dependencies. So we're building frameworks that allow us to understand how different teams' models relate. So it's kind of very basic provenance in the model serving framework. We allow for sharing of feature functions. So given that structure, we can then leverage the fact that multiple models use the same input and cache it and share that input across those multiple models. And then one of the things we're leveraging is this online learning. And this makes us slightly more robust to changes in features. So as things change, our weighting can change as a consequence of that. It's not an ideal solution, but it allows us to be, again, slightly robust when something downstream changes on us. With Dato, one of the things that we've done is actually focus on kind of a key, at least framework to understand why things are failing, which is much better metrics and login. So being able to capture how the models, the features, and intermediate loss, and so on are running within our modeling framework. We've also introduced an idea of model routing and aliasing, which I'll show you in a second. It makes it easy for teams to swap in and out models and to compete on different modeling techniques. In particular, we'll talk about bandits as a mechanism to allow multiple groups working on the same kind of problem to use their competing models to find the best solution, and to do that dynamically. And actually, I'll do that now, so the demo. So the Wi-Fi here is pretty good, so hopefully this will work. All right, so I don't know if you went to our booth. We have a demo. We call it the dress demo. So the idea is, let's say I was shopping for dresses. So I'm going to shop for dresses, and I enter dress, and it gives me a bunch of pictures of dresses. And we were thinking, wouldn't it be nice if I could click on a dress and find kind of dresses similar to that dress? So maybe, I don't know, let's say I was looking for this dress. There's some more similar dresses. And, maybe I click on, so I was actually showing this to my wife, which is a funny consequence. There's a bug in it, and I'll show you what I mean by that in a second, assuming this loads. So as I start to click on dresses, this is kind of similar. Maybe this one's pretty similar. You're starting to see maybe a pattern there as I click on these similar dresses. They're all red. So I thought this is a really killer demo, and I showed my wife, and she goes, yeah, I wouldn't use that, because all you've done is find red dresses. That doesn't help me, right? I'm interested in the style of the dresses. And I was actually kind of baffled. I don't know how to solve that problem. But it occurred to me, what if I was colorblind, right? Maybe I could make a colorblind neural net. If I was colorblind, I would at least fixate on red. So one of the things we did, and this is right before deadline, so we have a lot of time, was to build a colorblind neural net. So let me show you what it would be like as a data scientist if I wanted to put this in production and then kind of compete it against the existing neural net. So Dato Predictive Services has a nice Python interface, which is much easier to manage things. So I'm going to connect to it, hopefully. Good, so I've connected. We have a neat technology that lets you kind of actually visually interrogate your interface so you can see what's going on here. So I have a collection of endpoints, if it remembers. So this is actually a predictive service that should have, should have a bunch of different projects that we're running at the company. So we're serving a bunch of different models out of the system. So I have that running. And so I won't do this, I won't bore you with this today, but I built a neural net that has a colorblind filter at the beginning. So it's actually the standard ImageNet neural net, but I put a colorblind filter so it can't see color. So I'm going to take this colorblind neural net, and I'm going to deploy it. So I had already registered it in my system. That's actually another one line, but I have to have network to do it, so I didn't want to risk it. So it's already been uploaded. So I'm attaching my fresh dress more like image function to my colorblind neural net. So it was previously pointing to my my conventional neural net. I just switched it to a new neural net. And so instantaneously, the system is now colorblind, right? So if I click on, let's say, this dress, I start to see different colored dresses, right? And so now I might look at the different shape of the dress. And so I'm starting to see more diversity, right? Now I thought, well, maybe this is better. It's certainly not colorblind, but then these dresses don't look entirely similar either, right? So a better question might be, which one should I use? And how could I decide that more dynamically? Let's do that. So we can actually do an ensemble. So I'm going to actually deploy now a model which mixes these two models in production, right? So I'm going to point it at both my colorblind neural net and my standard neural net. I'm going to call it ensemble. So I just made a new model. Actually, we did an upload successfully. Hopefully. Good. So I've uploaded my model, and now I'm going to point. Excellent. I'm going to point my new neural net, or sorry, my fresh dress, more like image, endpoint at this new model. Right. So I just updated my REST service to serve a new model, which is a mixture of these models, which is actually going to be able to incorporate feedback. So it's going to look at what I click on, and I dynamically adapt to it. All right. So what's going to happen? So let's say I click on this red-looking dress. Give it a couple of seconds to load. All right, so we see some red dresses. We also see some other different color dresses. Let's say I actually really did like red. So maybe I clicked on red dresses. Actually, red wasn't the shape that I was looking for. It was really, it's the color. This is a different shape, but similar color. And maybe I do that again. Who knows if this will work? All right, so I'm actually giving it feedback, right? And as I click, I'm telling it, I do like red, but actually, it's red, it's all I care about. I don't really care about the shape, right? So maybe that's another red dress, different shape. So as I'm doing that, what's actually happening is the color-sensitive model is actually getting to pick more of the recommendations in the system. It's doing this automatically. And so if all things worked well, I can actually plot the current weights between the different policies. So the standard deep neural net, not the colorblind one, is getting to serve more of the traffic. Now, I've sped things up. We wouldn't want things to change this quickly. But it's actually taking this feedback and adjusting its trade-off between these models. Now, currently at Dato, we do this across your entire population. As I talked to you earlier, the idea of treating things at the level of sessions becomes critical when we introduce this adaptivity. And so one of the things that we're working towards, and one of the things that Velox really focused on, was the ability to do this not just for the entire population, but for me, and even in a particular session. So that's kind of an example of what I mean by these adaptive systems, learning in real time. All right, so let me conclude. So I've told you about a set of technologies being developed for this task of intelligent service design, this closed loop systems. Dato Predictive Services and the UC Berkeley Velox research project. And in particular, I talked about how it relates to these dimensions, which we need to start to think more about in terms of responsive, adaptive, and truly manageable model serving. And I think the key insights in these systems, if you think of Dato, it's really looking at caching in a new way, introducing bandits and new techniques and at least logging and managing our systems so we understand what's going on when they fail. And if you think of Velox, its key focus has been the split model formulation, decomposing our models into things that can be trained online and things that can be trained offline. All right, so in the last minute, I want to conclude by saying that I think the future of machine learning, and perhaps even data science, is moving in this direction of intelligent services, getting beyond this fiction of just going from a data to model and walking away or writing a conference paper, and instead thinking about how we serve actions and how those actions affect our data and how we incorporate those effects in our future models. Or more importantly, how we continually iterate on this process. With that, I thank you, and I'd be happy to take questions. Thank you. We're not. Give me a second. So one thing I will say is you're thinking, these technologies are both available. And so if you're interested, you should check out the Velox project is open source. It's still active research. And Dato is a production-ready system for doing model serving. And I think if you think of the space of machine learning, it's kind of unique in that it really connects to the ability to serve both our models and as we work towards the future, models from other systems like Spark. Actually, today it already serves the Dato create models and scikit-learn models in production. Yes?
You mentioned data and also AMP research. So what's the relationship of these two groups?
So what's the relationship between Dato and AmpLab? Me. I was a co-founder of Dato. I did a postdoc around the same time at the UC Berkeley AmpLab. I worked on a set of projects into we call BADAS, the Berkeley Data Analytics Stack, which has Spark. My project was GraphX and parts of MLlib, or I guess early iterations on that. The relationship now is that Dato can actually integrate with the Spark technology, so we can pull and talk with Spark. And in some ways, I think we're moving towards Dato being able to serve the models being developed in Spark. So if you train your model in Spark, we can serve it as well.
So any other questions you have, you can take it
Yep, thank you.
with the speaker. Thank you so much. Thank you.